Namaste. Welcome to this channel Chemistry Made Easy by Dr. ARM. We were discussing the molecular orbital theory, which is applicable or which is application of this theory to homo-nuclear diatomic molecules, in which we have seen the various homo-nuclear diatomic molecules starting from hydrogen to neon. In this case, we will see here what is the effect of nuclear charge on bond distance in homonuclear diatomic molecules of second period, means from boron to F2, that is fluorine. While moving from boron to fluorine, what is the effect of nuclear charge on covalent radius of these atoms? We have seen the molecular orbital diagrams of for these homonuclear diatomic molecules in detail in the previous discussion, and in that case we have seen that as we are moving from say boron or lithium, even lithium, to the neon, we are observing that there is increase in nuclear charge, as well as the number of valence electrons present in the corresponding atoms are also increasing gradually. As a result of this, with the increase in nuclear charge, the electrons are pulled much closer and closer to the nucleus, as a result of which the covalent radius goes on decreasing. But what happens here is, with this the bond distance is also changing, but that there is no a particular trend in distance, bond distance change, because there is effect of the valence electrons which are going into the bonding molecular orbitals, as well as in some cases they are going into the antibonding molecular orbitals. So whenever we are placing the electron in bonding molecular orbitals, it goes for increasing the strength of the bond, as a result of which the bond distance decreases. And as we are entering the electron in the antibonding molecular orbitals, every addition of such electron decreases the strength of the bond. Means, in other words, we can say the bond order decreases, and it goes on decreasing to the fluorine molecule, F2 molecule. So there is certain type of change which is affected by both the presence of bonding electrons or electrons going into the bonding molecular orbitals or antibonding molecular orbitals. Similarly, it is also affected by the nuclear charge, and this can be studied using the specific examples of this second period elements. So we will show this change in the form of graph. So we can draw this graph here like this. Say this is the axis along which we are showing this bond distance. So we are showing this bond distance here. Bond distance. So this is shown in picometer. And along this axis, we are showing the valence electrons. So we are showing here the valence electrons. So we can show these electrons here, starting from this 6, because when we are using the boron atom as the first atom, so in case of boron we will have the number of electrons like the 6, 7, then 8, then 9, then 10, then 11, then 12, and again we will add some 13, and $14 like this. So as a result of this, we will have these like this. So we can show this graph starting with the distance, bond distance from 100. Bond distance is used here for as 100 pm, 100 picometer at this baseline. Then there is next is 110. So this is 110. Then we will use this second line 120. Then this is 130. This is 140. Here it is 150, and 160. Like this. Now we can plot these values. So in case of boron, we will have this distance here. So this is B2 molecule. Then we will have C2 here having the value with 8 electrons at what 113. This is C2 molecule. Then with 9 electrons, that's N2. Here it is N2 plus. This is N2 plus. Then with 10 electrons, there is this 110 value for N2. Then O2 plus has 11 electrons. O2 plus, then there is O2 with 12 electrons, 121 plus here. This is O2. This is O2. Then here it is 13 electrons, 130 or O2 minus, O2 minus, and about 148 here it is for F2, and O2 minus. So in this way we will get here the trend showing the increase or decrease. So we can have the trend like this. So we have the trend showing like this. like this. So you can find here the trend like this. B2 molecule has 6 valence electrons, and these 6 electrons are going into the bonding molecular orbitals. So it has, B2 has 6 valence electrons which are going into the bonding molecular orbitals. So it has the bond order only with 2 electrons. So the bond order is only 1. So in case of C2 molecule, the bond order is 2. The valence electrons are 8. So as we are moving from B2 to C2, the nuclear charge increases, as a result of which the valence electrons are brought much closer to this. Similarly, the bond order increases, as a result of which the distance, bond distance decreases. So you will find that compared to B2, the bond distance is about 132 here ppm. Then if we go to N2, you will find that the bond distance again decreases to 110. Here this is because the bond order is highest here. Nitrogen, you know that the bond order in N2 is 3. The bond distance is shortest, that is 110. And here the valence electrons are 10. So all these electrons, valence electrons, are moving into only bonding molecular orbitals. So when every electron that enters into bonding molecular orbital, it contributes to 1/2 of the bonding effect. Means the bond order increases by 0.1 when 1 electron goes into bonding molecular orbital. And every electron that goes into antibonding molecular orbital, that cancels half of the bond formed. So this is the bonding effect and antibonding effect. So in case of, as we move from nitrogen to oxygen, here you must know that the bond order is 3. As we move to oxygen, the bond order becomes 2. And as we move from N2 ahead, here in case of nitrogen, all the bonding molecular orbitals are full with in all 6 electrons, and since there is no place for any more electron when we are considering O2, the electron moves into antibonding molecular orbital. So there are 2 unpaired electrons presenting antibonding molecular orbitals, as a result of which the bond order decreases by 1, which is here 3 and it becomes here 2. And as we move to fluorine, the bond order again decreases. It becomes 1 because the 2 more electrons enter into the antibonding molecular orbitals. As a result of which again the bond order decreases by 1 and the bond distance also increases. So you will find that from B2 to C2 and C2 to N2, the bond distance decreases. And from N2 to O2 and F2, the bond distance increases. This is because when we are going from B2 to C2 and to N2, you will find that the valence electrons are going into bonding molecular orbitals, as a result of which the bonding effect is enhanced. So the strength of bond is increasing from B2 to C2 and C2 to N2. But as we move from N2 to O2, the bond strength decreases, means the bond becomes longer and longer. So the bond distance increases and here bond distance decreases. So here with the decrease in the bond, with increase in the bond distance, you will find that the bond order also decreases and bond distance increases. So this is because every new electron enters into the antibonding molecular orbital. So this shows the effect of that the valence electrons are moving in here from nitrogen to fluorine into antibonding molecular orbital. Simultaneously you will find that with the increasing nuclear charge. So as we move from B2 to F2, you will find that there is increasing nuclear charge. So the electrons are pulled closer and closer. So the covalent radius, we will see in another graph, that decreases from B2 to F2. In case of oxygen, you will find that here is the bond order is 2. In case of N2, bond order is 3. But here you will find that by removing one electron, you will get N2 plus, and the bond order decreases by 0.5. So the number of electrons are 9, and the bond is, because of decreasing the strength of the bond distance increases. Here in case of oxygen O2 plus compared to O2, here by removing one more electron, the bond order decreases by 0.5, and bond is weakened, and therefore this the electron is removed from antibonding molecular orbital. In case of oxygen, there are 2 unpaired electrons in antibonding pi molecular orbitals. So out of that, 1 electron is removed, so the bonding effect is enhanced, and therefore the bond distance decreases here. And as we move from O2 to O2 minus, we are adding 1 electron to this antibonding molecular orbital. So their antibonding molecular orbital of O2 contains 3 unpaired electrons. As a result of which the bond order again here decreases, and it becomes 1.5. So because of this, the bond distance increases. The bond becomes weaker. Compared to O2, the bond becomes weaker. And again in case of O2 minus, so O2 minus, this distance is again increased. So here F2 is the bond distance is longest compared to this, but it is shorter than this B2. The bond order here it is 1. So in this way we can explain the effect of nuclear charge, and also the presence of electrons in whether bonding or antibonding molecular orbitals. We can explain why there is such change in the bond distance as we move from B2 to F2. Now we will see what is the effect of covalent radius. What is the effect of nuclear charge on covalent radius? So we can show this effect. So we can plot on this axis the covalent radius. Covalent radius in PM, picometer. And along this side we will plot this valence electrons. Valence electrons. So we have seen that the valence electrons are, as we have seen earlier, in case of atoms, we are considering here atoms and not molecules. In last paragraph we have seen the molecules, but here we are considering the atoms. So in case of atoms, if we take the atom that is boron, it has 3 valence electrons. Then next we have 4, 5, 6, 7, 8, 9, 10, etc. So in this, so we require only here up to 7. We don't need any more electrons. So if we compare this with boron, the boron has, so the bond is, the covalent radii are plotted here like this. 72 PM picometer. Here you will have 74. Then 70. Here it is 70. 70, 74, 78 and 82 PM. This is explaining PM. And we can have the values which are showing the graph like this. So boron is occupying this top position with 82. Here it is boron atom. Then we will have carbon with 4 unpaired electrons having the covalent radius having the value like this. This is for carbon. In case of nitrogen, you will have the unpaired electrons 5 and the covalent radius is like this. This is for nitrogen. Then for oxygen, you will have 6 electrons in valence shell and the value is like this. Oxygen. In case of fluorine, the value is like this. In case of fluorine, the values are like this. Now if we connect these points, we get the graph. Right. So here you will find that the covalent radius decreases from boron to carbon, carbon to nitrogen, nitrogen to oxygen and to fluorine. And if you see the valence electrons are 3 in boron, 4 in carbon, 5 in nitrogen, 6 in oxygen and 7 in fluorine. So here the nuclear charge also plays important role, means there is strong effect of nuclear charge on this covalent radius also. So as we move from boron to this fluorine, the nuclear charge increases and because of this the covalent radius decreases from boron to fluorine. In case of boron, the covalent radius is maximum. As we move to carbon, it decreases. Again to nitrogen, it again decreases. In oxygen and fluorine, it continuously drops down. And this is the impact of this nuclear charge. So nuclear charge has strong effect on this covalent radius. So covalent radius are decreasing in this way. So as we move from nitrogen to oxygen and to fluorine, or here also we will find that there is decrease in the covalent radius. But if we see the bond distance between this nitrogen, oxygen and fluorine, so you will find that the bond distance is having order like this. This has the order of bond distance. And this is because this order is observed because the valence electrons are moving into antibonding molecular orbitals, and this is having the effect on bond distance. So it has some consequence. The covalent radius has consequence on various bond distances. So if we consider the HF and if we consider the HF molecule and HO molecule, HF and HO, if we see the bond distance, we find that the bond distance are we can draw in linear fashion in this way. So HF, then HO, then HN, then HC and HB. So here you will find that the bond distance is decreasing in this way. The bond distance is decreasing from HF. Like this. So if we observe the actual values of these bond distance in PM, The values are 91.8. These are in picometer. So this is given in picometer. Then it is 96 in H2O, that is OH. It is 101.2 in HN, NH bond, and 109 in hydrogen carbon bond, and it is 120 in hydrogen and boron bond. So these bond distances are more than expected values. The values of the bond distance are larger than expected values of covalent radii. The changes are also still larger because of the additional bonds. So as we move from this boron to here fluorine, the bond distance, the additional bonds are observed. So as we move from here in this direction, there are increasing the bond, increasing the bonding or bond multiplicity increases. So because of this, here you will find that there is only sigma bond. Here you will have the bonds having some additional characters, means additional value. So it is more than 1. Here it is more than 2. Like this. So the bond distance is also increasing. This is because the values are increasing. Means bond distance decreases in this direction because the number of bonds or bond multiplicity increases in this direction. So there is increasing bond multiplicity. Bond multiplicity increases in this direction. And that is why we are observing this effect. Means single bond, double bond, triple bonds, etc. So such bonding effects are observed, and that is why the covalent radii are also found to be decreasing in this direction. So with this we will stop our discussion. Thank you very much for watching this video. Please subscribe to this channel and press bell icon and like button. Thank you very much.